All right, section 3.5. Here's our second part of optimization. All right. So we looked at kind of the basics of optimization in that previous section, where it really comes down to either in maximizing or minimizing a function. It's all about finding the critical values, all right, and then checking to see if those are the locations of maximum or minimum values of our function. For this section, we're going to look at a few different applications, a little more involved than the applications we looked at previously. These are called optimization problems, obviously, because we're looking to find an optimal or maximum or minimum value of a function. And these are really good examples of real-world applications. I mean, this is the type of stuff that goes on a day-to-day basis in the business world, in manufacturing, etc. Calculating costs or price, determining profits, revenues, all of these types of things. As we keep saying, there's a lot of real-world application for this stuff. Now, these are a little bit more involved, a little bit more complex for two reasons. First of all, you're going to be dealing with multiple variables, at least initially. Secondly, you're going to be dealing with multiple equations, right? But here's the idea. You have what is called an objective function. This is going to be the function, the quantity that we're looking to optimize, right? So it's the quantity that we're trying to find the maximum or minimum value for. We're also going to have what's called a constraint. This is an equation or a function that provides a relationship between the multiple variables that we're going to have to deal with. Because typically, objective functions contain more than one variable. All right. And in our case, we're going to be limited to two. In the real world, you can have many variables involved in optimization problems, because there's a lot of factors that affect these different outcomes. But for our case, we're starting off kind of simple. So we're going to have objective functions that involve two variables, right? And then the constraint is what allows you to rewrite that objective function in terms of one variable. So if I have an objective function involving two variables, and I have a constraint, which is another equation that gives me a relationship between those two variables, then I can solve that constraint for one of those variables and sub it out in the objective equation. Now, once we do that, we're going to end up with our objective equation or our objective function containing a single variable. And then we're just going to be back to business as usual at that point. We'll go back, that's the function we want to maximize or minimize, find the critical values, check to see if it's max or min, and so on, right? So really, the bulk of this is all about being able to take your objective function, use the constraint to write that objective function in terms of a single variable, and then we go about our normal business. So example number one. We've got a rectangular garden with an area of 1,200 square yards. It's to be enclosed on two parallel sides by a stone wall that costs $35 per yard. So two sides of my garden are going to have a stone wall, the cost of which is $35 per yard. And on the other two sides, we're going to put wood fence. And the wood fence costs $28 per yard. First, what are the dimensions that would give us the minimum total cost? Right? So we want to construct our enclosure for the minimum amount of cost. And then what is that minimum cost? Right? So of course, initially, I want to know what my dimensions would need to be so that my cost is at a minimum. And then what is the minimum cost for actually constructing the enclosure? Now, there are some implied limitations, at least initially. I mean, I'm looking at a rectangle, which are typical dimensions on a rectangle, length and width. So I've got L and W initially. And we know those are going to be positive values. So we always talk about with applications how there are typically some implied limitations or restrictions on your variables. And in this case, we're looking at length and width of a rectangle, which both have to be positive values. Now, what I did in this case, and when you're dealing with multiple variables especially, The labeling of the variable, you all of course want to be clear as far as what each variable represents, so that when you go back and answer questions, you know exactly which variable or which quantity you're talking about when you're answering the question. So my rectangle, I have length and width. I went ahead and changed L to S, and I'm letting that represent the two sides that are constructed from the stone wall. And then I'm just going to leave W to represent the sides that are constructed with the wood fence. All right, so S is for stone and W for wood. You can always use whatever variables you want to use. When you're labeling these things, you just want to be clear as far as what each variable represents, so there's no confusion when you go to answer your question as far as what quantity you're talking about. All right, so now, what are the equations or what are the functions that I can use? Well, since we're talking about minimizing the cost, we need a function that I can use to calculate the cost of the fencing, right? Well, we've got two sides made of the stone wall. We've got two sides made of wood fencing. Well, if I'm constructing a rectangular region, well, how about we talk about the perimeter of that thing, right? Because there's four sides. Two sides times the length and two sides times the width, or in our case, I'm using 2S and 2W, 2 times the sides of stone walls plus 2 times the side of wood fencing. We're also given information about the area of this rectangle. We're told in the original problem that the area was 1,200 square yards. So here is an equation that relates the two variables, S and W, all right, in another way, and that area equals S times W for a rectangle. Now, since my objective function has to be my cost function, right, how much does it cost to build the fencing or to build the enclosure? I'm going to go ahead and call that function C, and I'm using our perimeter because the cost is going to be two sides times $35 per yard of stone wall plus the two sides at $28 per yard of wood fencing, right? So the cost, $35 per yard of stone wall, $28 per yard of wood fencing, and I'm just plugging that into the perimeter. How much of it do I need? And so that would construct our cost function, which is our objective function. That's the one that we're trying to ultimately minimize, right? We want to define the minimum cost. So first I just simplified that when it multiplied, and so I've got a cost function C equals 70S plus 56W. Now, that's our objective function, but it contains two variables, S and W. We need to then, your next step in the process, we need to express that function in terms of a single variable. And that's where the constraint comes in. That's where that other relationship comes into play, the fact that we know the area of that rectangle to be 1,200 square yards. So that's length times width, or in this case, S times W. And then I take that constraint and I solve it for one of those variables. Now, it doesn't matter which one you solve for. Typically, we solve for the one that's easier to solve for. In this case, it really doesn't matter. You're going to divide 1,200 by S if you solve for W. You divide 1,200 by W if you're solving for S. But it's really, it's irrelevant. It's your choice. You just need to solve that constraint for one of your variables so that you can then come into your objective function and sub out one of those variables. So I took the constraint function, solved it for W. I then went into my objective function, which is our cost function, and I replaced W with 1,200 over S. Now our cost function, which is the one we're trying to minimize, is a function of one variable. We're back to business as usual now. All right, now I've got a function that I'm looking to minimize. I'm finding the minimum value of. All right, so like I said, that's the new stuff here. That's the bulk of the work, is being able to take or construct our objective function, form our constraint equation that I can use to sub out one of the variables in the objective function. And then we proceed normally from there to find the minimum value of that function. All right, so how do we do that? Well, the first thing I did, I just rewrote the 1,200 over S times 56. I went ahead and just multiplied those two to give me the 70S plus 67,200 over S. And then I rewrote it as 70S plus 67,200S to the negative 1, because my next step, since we are looking to minimize this function, is to find our critical values. And I'm going to find the critical values, remember, by finding our derivative and then setting our derivative either equal to 0 or where the derivative is undefined, right? So now we're back to the mechanics of this thing in terms of finding our critical values of the function, right? So continuing, here's our cost function again. That's the one I just wrote. We want to find our critical values, so we want to minimize that function. So we find our derivative, c prime. And again, that's a nice little power function. So 70 minus 67 to s to the negative 2 using our power rule. And then we find our critical values by setting that derivative equal to 0. And then I solve that equation. So first I just rewrote it as 67,200 over s squared. And then we're solving that for s. So I added 70. And then multiplied both sides by s squared. Divided by 70. And now I've got s squared equals 960. And then the square root of s, or square root of 960, approximately 31. Now, of course, typically I would have the plus or minus the square root of 960, but again, context, s is the amount of stone wall that we need to form our rectangle, or at least one side of it. We know that's, like we said, our initial limitations, that has to be a positive value. So, yeah, generally speaking, there is a positive and negative square root, but we're only interested in the positive because of the context. Well, that's our critical value, right? So then we said, okay, we need to check to see if at that critical value, we actually do, in this case, have a minimum, right? Now, here's a little heads up with these. If you set up your objective function in one variable, and you find your critical value, and you end up with a single critical value like we do in this case, that is typically going to be either the maximum or minimum for your function, depending on which one is applicable or which one would be appropriate, right? In this case, we need to see that that is a minimum value, or where the minimum value of the function occurs. So we can check that like we did before. You know, we use that little test strip and said, okay, I have a CV at 31, so I'm just going to plug in values to the left and to the right of 31 into C prime to check the value of C prime to see if it's positive or negative. And if you plug in 30 into C prime, you will get a negative value. You plug in 32 into C prime, you do get a positive value. So that tells us that what the function is decreasing on the left side of 31 and it's increasing on the right side of 31, which means at 31 we have a minimum, right? So again, that's our basic process. But just a little heads up with these. In solving these particular problems, if you end up with a single critical value, I guarantee you it's going to be either the minimum or maximum, or the location of it, at least, whichever is relevant to the particular problem. But we always say let's double check it just to make sure. Now remember, you could also use the second derivative to double check, right? If you care to do that, to see if that is a minimum or maximum, just to refresh. If we have the second derivative, or find the second derivative, C double prime. And when you plug in your critical value into the second derivative, if it's a positive value, then that means our function is concave up, which means there's a minimum there. If you plug that critical value into C double prime and you get a negative value, remember the second derivative tells you about concavity, that means the function would be concave down, which means at that point there's a relative maximum. Right? So I mean, you can use second derivative if you wish. I'm using first derivative because, I mean, I always say, why bother doing the second derivative when you already have the first derivative? And that works fine. But anyway, so there's our minimum value. We know it occurs at s equals 31. Now that's s, that's the length of the stone wall side. So I need to also find the amount of wood fencing that we need, or at least the dimensions of the wood side. So we have s equals 31. We can go back to our equation that we solved previously. I have w was equal to 1200 over s. So I just simply plug that in, and I've got a value for w of approximately 38.7 yards. Okay. So that gives us the dimensions of our rectangular enclosure that would minimize our cost. We know what the minimum cost would occur for dimensions of 38.7 yards on the wood fence side by 31 yards on the stone wall side. And then we were also asked for the minimum cost. I'll just plug that back into my cost function, right? So once we find the value for S and W, we'll just plug that back into our cost function, and we get a total cost of approximately $4,337 to enclose our garden with the 2 stone wall sides and the 2 sides of wood fencing. But that is a typical optimization problem. Right? A couple of other examples just to show you some different variations on things. Example number 2. For this one, again, we are given a cost function, so C of X equals is our cost function for a certain product, where X is the number of units produced. Let me highlight my cost function. So that's the cost of a product, where X is the number of units produced. We're asked to find the minimum marginal cost. Now, we've talked about marginal cost before. Remember, marginal cost, that's your derivative. That's the rate of change in your cost function. But more specifically, the marginal cost, we said, was the cost of producing the next unit after X number of units have been produced, right? So, for example, if we produced 20 units, we could find the marginal cost at a production level of 20 units, and that would give us the rate of change at a production level of 20 units, which would tell us how much it would cost or how much we would expect it to cost to produce the 21st unit. Right? So yeah, we've talked extensively about marginal cost, so I want to just remind you exactly what that describes. Now, in this case, we are looking to optimize, minimize in this case, our marginal cost. So that's our objective function. Right? Now the marginal cost, again, that's C prime. So my marginal cost function, which is going to be my objective function, is the derivative of our cost function. So C prime is 3x squared minus 12x plus 13. And that's the function that we want to minimize. So there is our objective function. I think I wrote that down. Let me. So that would be my objective function in this case, because that's the function that we're looking to minimize. Then, in this case, since we are, our objective function is only constructed using one variable, that saves us from having to deal with or look for any type of constraint. As long as my objective function contains a single variable, like it does in this case, just x, we can proceed normally. Now, here's where things can be a little bit tricky, but you have to you have to watch the context. You have to look at which function you're talking about. Here, where I am looking to minimize my marginal cost. I'm looking to minimize C prime. If we were looking to minimize the cost like we did in the previous example, then we would find our critical values using C prime. Here, we're looking to minimize C prime. So I would use the critical values for C prime, which would come from our second derivative, right? Because again, this is C prime, it's also our marginal cost. So the derivative of the marginal cost, which is what we use to find our critical values, is also then the second derivative of our cost function, right? So you have to be careful. Like I said, don't get caught up in the whole, first derivative, second derivative thing and what each one of those tells us. It's all relative to the function that you're working with. And if I'm working with cost, I use the derivative of the cost function to find its critical values. If I want to know the critical values of the derivative, then I use the second derivative, right? Which is its derivative. Say that 3 times fast. But regardless, I need the second derivative, which would be 6x minus 12, to find the critical values of our first derivative, which is our marginal cost function. So 6x minus 12, setting that equal to 0, we get x equals 2. That's our critical value. And now again, I need to check to see if that is actually the location of a minimum value. And I'll tell you it would be because there's only one, but we can double check. So I set up my test strip with our marginal cost prime, which is C double prime. I plug in 1, plug in 3, a number to the left of 2, a number to the right of 2. If you plug in 1 into that second derivative, you will get a negative value. You plug in 3, you get a positive value. So that tells us again that our marginal cost function is decreasing on the left of 2 and increasing on the right of 2. So it would be the location of a minimum. So C prime of 2 is a minimum value. That's our marginal cost function. And then the actual value, C prime of 2, we plug that in. We get a value of 1. Right? So that's plugging that into our marginal cost function. So that is our marginal cost, which is our rate of change. Right? So what is our minimum marginal cost? Now remember, marginal cost, that's the price per unit, right? Because it's our cost per unit because it's the rate of change in the cost. So my marginal cost, or the minimum marginal cost in this case, would be $1 per unit. Right. So it's a little bit different in the context of, or in the sense that, we're not just taking a function and using its derivative, we're actually using the derivative and then the second derivative. But it's all relevant to which function you're actually trying to optimize. Next example will bring up maybe an interesting question or a couple of interesting questions. So let's say, for example, 3. Suppose that the monthly cost in dollars of producing X chairs is given by that cost function, C of X. And currently, 50 chairs are being produced per month. Right? So we have a cost function for producing X number of chairs. Our current production level is 50 chairs per month. Question part A. What is the current monthly cost? Well, we're producing 50 chairs. We have our cost function, so I'm just going to plug 50 into our cost function. C of 50, $1,295. That's our cost of producing 50 chairs. Question part B. What would be the additional cost if we increased production to 53 chairs per month? All right, so instead of 50 chairs per month, let's increase our production to 53 chairs per month. What is the additional cost? Well, we already found the cost of producing 50 chairs. We could simply then find the cost of producing 53 and plug that into our cost function. And we take the difference of the two. And so if I plug in 53, I get whatever I get. Subtract out C of 50. You're going to get a difference of $117.38. Now again, what is that? Well, that's the additional cost of producing 3 extra chairs, right? So going from 50 to 53 in our production level. Now, here's the thing. The cost function that we have, C of X, that's the cost function that was calculated or determined based upon the current production level of 50 chairs per month. The question would be, or here's the first question to think about, especially you business majors. If you change the production level, would your cost function change? Now, not just the cost. We know that's going to change, right? Because if I produce more chairs, then I'm going to have higher costs. Right? That's obvious. But the way that we would calculate our cost, does that stay the same if we change our production level, right? So think about that for a second. We're going to address that as we go forward. So my point is, we're assuming here that cost remains unchanged, right? Or that our cost function doesn't change if we change our production level. All right, so we have an additional $117.38 if we raise our production level to 53 chairs per month. Part C, what's the marginal cost when X equals 50? All right, so again, there's our marginal cost, which is our derivative, that's C prime. So C prime, we can find that easy enough. Again, nice little power function using power rule. And then we want our marginal cost at our production level of $50, or 50 chairs, excuse me. Plug 50 into that's the marginal cost, and I get $38 per chair. Okay. Rate of change in the production of chairs. Now remember again, what is marginal cost? Marginal cost gives you the cost of producing the next item after X items have been produced. So to say that C prime of 50 is $38 per chair, that means that we're looking at an increase of $38 or a cost of $38 to produce the next chair after 50 chairs have already been produced. Because again, that's the rate of change in your cost. Now look at part D. Use the marginal cost to estimate the difference in cost of the production if we increase from 50 to 53 chairs. Now we did that back in part B. All right. We said, what's the cost, or what would be the change in cost if we increased our production level from 53 to 50 chairs? So we took C of 53, we subtracted out C of 50, we got $117.38. Part D is asking us to use the marginal cost to make that same determination. So if I change from 50 chairs to 53 chairs per month, the marginal cost says that it's going to cost you an additional $38 per chair after 50 chairs have been produced. Well, if we go from 50 to 53 chairs at X equals 50, marginal cost is $38 per chair, which means we're looking to, or an additional cost of $38 after 50 chairs have been produced. So to produce 3 more chairs, 3 chairs at $38 a piece, we've got $114. And according to the marginal cost function, that would be our change in cost if we increase production from 50 to 53 chairs. So notice the difference between parts B and D. Part B used the original cost function, which was based on a production level of 50 chairs. And according to that model, it would cost an extra $117.38 to produce 3 more chairs. According to the marginal cost, which is the rate of change in the production costs, it would only cost $114 to produce 3 extra chairs. So we get 2 different answers there. So I guess my question would be, which one do you think is more accurate? Right? Well, probably the second one, because the first one is based upon a fixed number, and we say, okay, after we produce 50 chairs, here's our cost function. The second calculation that we made was made on more of a fluid change in the actual cost. Right? So I mean, things changed. Costs don't stay the same. If you're going to change your production level, there's a lot more variable or variation that comes into that. A lot of things that affect that, right? So yeah, this and again, this is a very simple example, but this gives you a very kind of a simple taste of the types of things that have to be dealt with on a daily basis in the real world, right? And again, this is why every company in the world employs a fleet of mathematicians. Like, what do I ever do with a math degree? Well, you can get a pretty decent job with a pretty good company, because those are the guys that figure out this stuff, right? So, and there's a lot of different variation, a lot of different variables that go into play anytime you're calculating those types of quantities, right? So it's not a simple thing. Example number 4. Now, this one's going to be a little bit trickier, but I want to give you an example of another situation. You'll see one similar to this in your homework. But it's a little bit trickier situation. So for number 4, when a theater charges $5 for admission, there is an average attendance of 180 people, right, per show. For every 10 cents increase in the admission price, there is a loss of 1 customer from the average attendance. Right. So, in other words, they determined that if they charge $5 per ticket, that on the average they get 180 people per show. But if they increase the price by 10 cents, so let's say we charge $5.10 a ticket, then they would expect a loss of 1 person, 1 customer on that average. So the average would go down to 179 per show. Right. So an increase in price obviously would lead to a decrease in the number of ticket sales. Okay. Our question is, what admission price should be charged to maximize the revenue? Now, here's another interesting question. All right, so maximizing revenue. Now, in the business world, what do you think is usually the primary objective? It's maximizing profit, right? They want to make the most profit possible. That's usually the objective of most businesses. Here we're looking to maximize revenue. So here's another question to think about. Does maximum revenue mean maximum profit? Are those one and the same, right? So, I mean, initially you think, okay, if I increase revenue, I'm probably going to increase profit. But remember, there could be a lot of other variables that affect that. Maybe more revenue means that I have to produce more product. And maybe my production costs get larger as my revenue increases, but possibly my profit could go down because remember, profit is the difference between revenue and cost. All right, now that's kind of an aside. It's just something else to think about. It's more, again, to give you an example of how complex all this stuff is and why us mathematicians are so important to the existence of the world. Right? So when you talk max revenue, you're not necessarily talking max profit. Right? Now maybe there's a direct correlation between the two, but not necessarily. All right, so for our purposes, we'll get back to the business at hand. Now it's kind of an aside, just something else to think about. So we are looking to maximize our revenue. So we need a revenue function, right? So that becomes my objective function. Well, how do I calculate the revenue? Well, initially, at least in this case, revenue, and we've talked about this situation before, in the middle of other things, so I want to emphasize this a little bit. This revenue function, R of x equals P times x, right? What is our revenue? Well, in this case, it's the number of attendees, right, which would be the number of tickets that they sell, times the price of admission, right? So price of admission times number of attendees, P times x, gives us our revenue. So there's our objective function. Revenue is the price per ticket times the number of tickets sold, or in this case, we'll call it the number of attendees. Now, implied restrictions, x and p, both are positive. Again, and that's usually the case with most variables that you're dealing with in real-world applications. They're typically restricted to be positive values. Now, in this case, I guess x could be 0, because if you don't have anybody attending, maybe I raise the price too high, or I have a show that nobody wants to see, I could have no attendees, right? So x is greater than or equal to 0. The price is positive, unless you want to charge free admission and not have any revenue, I guess. But those are just, again, implied restrictions on those variables. That doesn't help me in constructing my objective function. I still have two variables there, p and x. So we need to construct R of x in terms of a single variable. So I either need to get rid of p and put that in terms of x, or I need to put x in terms of p. All right, so typically, though, with a case of this type, if we've got the price times number of attendees or number of units, I'm going to look to express that price function as a function of x, as a function of the number of attendees. Now, we're calling it a price function. It's also called a demand function. And that's something we're going to explore more in detail in the next section. We're going to talk about demand functions, but it's a price function, I mean, because the price that you charge is going to be based upon the demand for the product. And in this case, it's the ticket to a show. And so I'm going to charge a certain price for that ticket. Depending upon the price, there's going to be a certain amount of demand. If the price is low, demand is going to increase. If prices go up, demand is typically going to decrease. Okay? But regardless, it's all based upon how many people are willing to buy the ticket at the price that we're charging. So we call it a demand function. Price function, demand function, same thing. Now, these are typically linear functions, not always, but for the limited amount of information that we have, we can construct a linear function to represent this price function or demand function in terms of x, in terms of the number of attendees or the number of tickets sold. So now what do we know? We know that x equals 180 when p equals 5. We know that there's an average attendance of 180 people at a price of $5. We also know that there's a rate in change in the demand for the tickets. That if we change the price by 10 cents, that there was a decrease in the number of attendees. So that's a rate of change in our demand. Our demand goes down when the price goes up. So an increase of 10 cents per ticket gives us a decrease of 1 in attendees. Right? So that'll give us a negative 0.10, which is the rate of change in our demand or price. Well, that's our slope, right? Because that's what rate of change is. So if I'm constructing this linear equation to calculate the price or demand in terms of x, there's my slope for that function, negative 0.1. And I'm using a relationship between price and number of attendees, right? So I could use x as my input, p as my output, set up an ordered pair with the information that we have. 180 is my attendance, x, p is my price, $5. And we have this slope, this rate of change that relates the two, price per change in attendance of negative 0.10. Now we're just constructing a line. We're constructing the equation of a line. And I went ahead and used this, and some of you use the slope-intercept form, but I've always used the point-slope form, so that's what I'm going to use here. The only difference is instead of y, I've got p. Right. So x is my input, number of attendees, y is my output, which is my price. So I'm just going to replace y with p. So now I've got the equation p minus p sub 1 equals m times x minus x sub 1, where again, remember, you're always plugging in the known quantities in place of the variables with the subscripts, so p sub 1 and x sub 1. So replacing p sub 1 with 5, that's the price that we have. Replacing x sub 1 with 180, that's the attendance that we have at that price. And then replacing m with the negative 0.10 that we just found. So there's my equation, p minus 5, negative 0.10 times x minus 180. We're just solving that for p, so that I now have a price or demand function in terms of x. So p equals negative 0.10 x plus 23. I can now take that back to my objective function, which, remember, r of x, revenue was my objective function. It was p times x. And I can replace p with negative 0.10 x plus 23 times x. And then I just went ahead and distributed x to get our revenue function in terms of x that we are looking to maximize, because that was our original question. We wanted max revenue. So now we're back to normal business from here. I finally have my function that I'm looking to optimize. Like I said, that's the bulk of the work. It's getting it to that point. And now we just follow through with finding the maximum or minimum value. So we find our CVs, so r prime, and find our derivative, again a nice little power function. Set that equal to 0 and solve it. And I get x equal to approximately 115, or I think this comes exactly 115 attendees. Now, what is that value for x? That is the critical value of the revenue function. And I didn't write this, I'm going to put it in additional here. We said we want to actually make sure that that is where we have the maximum value for our revenue function, right? Because that's our critical value. So here's r prime. That's where it's equal to 0. And then we said we would typically, plug in something to the left and to the right. So let's say maybe 114 and 160. Right? So if you plug in 114 into r prime, you should get a positive value. You could double check that. 114 times 0.2 would be 2.28, and that's negative. So negative 22.8, excuse me, plus 23 give me a positive value. If we plug in 116 into r prime, that would be 116 times 0.2 would give us 0.2. Now again, that's negative, so negative 23.2 plus 23 gives me a negative value. But you can double check that. But I do get a positive value if we plug in something to the right, or to the left rather, and a negative value if we plug in something to the right of 115. So what does that tell me? That tells me that revenue is increasing on the left and decreasing on the right of 115, which makes 115 the location of a maximum. So revenue is maximum or maximized with 115 attendees. And then what would the price per ticket be to maximize the revenue? Well, there's our price function, the one that we just found right here. And I can plug our 115 into that price function, and that will give you $11.50. Right? So remember the initial information, we had an average of 180 attendees at $5 per ticket, and we had the relationship that if you increase by 10 cents, you would decrease the number of attendees. So this is telling me that if we charge $11.50 per ticket or per admission, you're going to have 115 attendees. Even though you've got fewer attendees, you've got the maximum revenue there. Right? So that's the game that you have to play. You adjust the price and adjust accordingly to increase revenue, to maximize revenue, maximize profit. That's the game that gets played in the real world. Right? All right, that's section, what is this, 3.5?